Well, hello, and welcome to the 13th U.S. Permafrost Technical Training Webinar. And today we have the great pleasure of having Professor Pooneh Maghoul to give us a talk on the permafrost carbon feedback from site processes to regional predictions. Well, the format of today's webinar is I'll give our first a brief introduction, and then Professor Maghoul will give us about 40 to 45 minutes talk, and then we'll leave the last about 10 minutes on the question and answers. And the 2025 USP webinar series is sponsored by the Arctic Foundation's P&D engineers, Shannon and Wilson, and WSP. And first, I want to give a brief introduction. Um, Dr. Pooneh Maghoul is a full professor of geotechnical engineering at Polytechnique, Montreal, and the director of the Sustainable Infrastructure and Geoengineering Laboratory, or SIG Lab. Her research focuses on the resilience and sustainability of northern and permafrost-affected infrastructure under climate change. She also serves as the lead for sustainable infrastructure in cold regions at the United Nations University Institute for Water, Environment, and Health, or in short, it is UNU-INWEH, that's acronym, where she bridges engineering science with policy to support sustainable development in cold and Arctic regions. Dr. Maghoul is a recipient of several national and international distinctions, including the Honoris Genesis Award for research or teaching from the Orders des Ingénieurs de Quebec, or OIQ. I guess that's how a Chinese trying to speak French in English. And the Outstanding Young Geotechnical Engineer Award from the International Society for Soil Mechanics and Geotechnical Engineering, or ISSMGE. So with that, Pooneh, Dr.
Oh,
Maghoul,
thank you
thank
very
you so
much.
much.
Thanks, Dr. Gio. And by the way, your French pronunciation was just wonderful.
Thank you very
I
much.
loved it. Thank you very much for
Mm.
the opportunity. And I'm very pleased to be with you today. Thank you very much for having me. Yeah, I'm based in Montreal at Polytechnique Montreal in Quebec, and we speak French and English too. Then this is the title of my presentation, Permafrost Carbon Feedback from Site Processes to Regional Predictions. I've been actually working on this topic since 2021-22. And what I'm going to present you, there are some preliminary results that we obtained. And just to tell you that this research is ongoing, then if you are interested, I would be more than happy to collaborate with you all. Let's start. I'm also just taking time. Then this is United States Permafrost Association. For sure, I don't need to define permafrost, but for some, let's say, formality, let's do it. We know that we define permafrost as ground that remains at or below 0 degree for at least 2 consecutive years. And we call the top layer of permafrost active layer, which undergoes seasonal freeze-thaw cycles. And at this in engineering, from engineering viewpoint, most of our problems, are related to managing, this active layer. And what happens with climate change is that it gets more and more thickened, depending on the region, the impact of climate change, etc. That thickening becomes really problematic for us. Then the thickness of this active layer depends on many factors like climate, local and climate conditions. For example, what's the vegetation, what is the soil type, what is air temperature. In some places, for example, climate change from measuring air temperature can be really, really harsh, but soil type is not bad. I mean, we have like coarse grained soil, so the impact of climate change for us can be like low to moderate. But in some locations, we can have moderate, impact of climate change in terms of temperature, precipitation, etc. But soil is problematic. It's like, we have frost-susceptible soil. We can have ice-rich permafrost, and the impact of climate change in terms of risk can be high. So you see that local conditions and also climate conditions can both have an impact on the thickening, of the active layer. Then what happens with climate change in these regions is that we have permafrost thaw. We have, as I said, the increasing the thickness of active layer in many different permafrost sites. We have now retrogressive thaw slumps everywhere, and my topic will actually focus on permafrost carbon feedback. How this mass loss can also contribute to permafrost carbon feedback. I took this video from a colleague that I really respect, Brandon, and you see that he took the permafrost samples, in the lab, and you see that it's at room temperature, and you can see that warming, thaw settlement. And you see that, for example, the one here at right, you see that it's a kind of coarse-grained permafrost. Then we see thawing. It's, that we should always say permafrost thawing, not permafrost melting. But the one at left side, you can see that it's like a kind of ice-rich permafrost. And just imagine we have a building or infrastructure, road or something like that. Energy facility on top of this, ice-rich permafrost, and you can imagine what will happen. So in terms of, the Arctic warming or let's say a climate change in northern regions, I remember 2-3 years ago, what we had in mind is like the rate of warming in northern regions is twice, then 3 times. Now, in 2025, 2026, the numbers we should communicate, it's like 4 times, 5 to 7 times the global warming averages. Then it's just, in the matter of few years, like 2-3 years, you can see the increase we can see in terms of, temperature. So if we want to see at really regional scale, countryside, the scale, this is a map of Canada. And I'm sure that in the United States or somewhere else, it's actually the same thing. We do not have one type of permafrost. We have continuous, discontinuous, sporadic, isolated, like ice patches within soil layers. And again, I repeat, climate change pattern is different from site to site. Soil type and vegetation type different from site to site. And soil type different. And bad news is that it's not like constant. I mean, when we talk about vegetation back in 2010 may be different from 2025, 2026, or even 2040, in the same site. So if we want to propose like climate adaptation strategy, what type of vegetation we should actually plant? There are so many uncertainties, regarding these things, regarding infrastructure design. What makes, this field permafrost engineering so interesting because of these uncertainties and challenges we have. We did the study with one of my former PhD students. We developed an AI platform, machine learning platform, and what we tried to do is to use this, the big data, use this, machine learning, advanced machine learning algorithms to predict ground surface temperature, not air temperature. Air temperature we can download from all these, climate models, different scenarios. But what is really problematic, in permafrost engineering and management is ground surface temperature. Then we have different approaches to calculate it. We have like N factor, we have like energy balance. But something which is again problematic is that what we call it climate non-stationarity. N factor and energy balance, they are very, practical approaches in engineering design. But again, N factor deals with like static data, stationary data. But if we want to have an idea about, the climate warming in 2050, 2060, even that N factor is a constant. We don't know how to handle it. That's why it can be one of the advantages of AI, that it can actually self-fit itself, from the past and current data, we can use it. So I don't want to present our model today. I just want to show you this graph. It's from different, the cities, villages in Nunavik, north of Quebec. And we are back in here in 2025. You see, the color changes, how actually the climate warming, these reddish, orangish color becomes like more intense, especially beginning from 2030. Then, as I told you, it's from different locations in Nunavik, north of Quebec, ground surface temperature. We validated our model with many field data. And as I told you, we can also improve the accuracy of our model. So that was for the temperature. The other thing that I just told you about, the impact of vegetation. I told you climate change patterns, the change from site to site, soil type changes, also site to site. But soil is soil. It's like each place, each site has its own stratigraphy and soil profile. Then you can characterize it, even though it's dynamic, because permafrost changes, active layer, etc. But what I want to tell you here is that greening and afforestation that is happening now. We have done recently a study with one of my PhD student, Daniel. Our work we submitted is under review now, but here I just took one figure from our paper just to show you this, the vegetation changes over time. Then in short, if I can present you these, panels at top show where vegetation is changing and how fast. Then it shows like time difference from 1986 to 2023. It's based on NDVI, which is a kind of satellite, measure for plant greenance. It's an indicator of that. And this one shows the exponential, the greening, not linear, exponential. Then you can feel that, how fast, this vegetation pattern landscape changes. And the panels you can see here at bottom, they show what kinds of land changes are causing that vegetation change. So if I want again to come back to that panel one, it shows where plants are getting greener or browner based on the indicators that I actually present in here over time. And we use, a kind of a statistical test, Tailson and Kendall, which helps detect whether the NDVI is increasing or decreasing. And panel B shows the same trend, but as I told you, we used an exponential curve to model, which helps visualize, the rate of change more smoothly. Just to tell you, climate change again, permafrost thaw, and the other problem we have is, I don't know if we should say a problem or not, but it's a fact, it's that greening. And not only we see more greening, but we also have the change in the type of vegetation. We have shrub and, the trees, etc. Different things that, is happening now. That 10 years ago, 15 years ago, we didn't have the same vegetation type. So the other thing I want to mention is, about the permafrost carbon. Today, what we estimate is that we know that permafrost is like represents the largest source of terrestrial carbon sink, the largest one, carbon sink. And the question we have to answer, where are, you know, these carbon pools? Then we divided into 3 different categories within the top 3 meters of the ground, carbon in deposits deeper than 3 meters, and also permafrost carbon or gas hydrate bearing sediments that you probably heard that are actually on shallow submarine shelves in the Arctic. So what I'm going to present today, we really focus on these top 3 meters of the ground. And what is important, you know, in that, you know, a layer is that we know that nearly half of the soil organic carbon, or SOC, in the northern, you know, regions is situated in the top meter of the soil. Half of the soil carbon, you know, soil organic carbon in permafrost regions is situated at the top, you know, 1 meter. And the other thing is that near surface permafrost soils, we define it, you know, between the surface and 3 meters deep, contain about 1,000, let's say 1,100, around 1,100 PG carbon. And what is PG? We define it as 1 billion tons. Then this is huge. And we also, you know, have another interesting number here, that we say that it is that, you know, the amount of carbon is equivalent, you know, of 33% of the global carbon pool, which is actually stored in the permafrost region. Then permafrost region, you know, it just covers 15% of the total global soil area, but it contains 33% of the global carbon pool. Then these amounts, how we actually get it is that it's about 2-fold the amount of carbon that we have in the atmosphere today. And how we got that 33%, it's just, we know that the amount of, you know, the soil organic carbon in near surface soil layer, top 3 meters, of the rest of Earth's biomass. We exclude Arctic and boreal regions, you know, all the globe on Earth, the top 3 meters contain about 2,050 PG carbon. So if we calculate, you know, the amount of carbon that we estimate today at the top 3 meters, as I told you, 1,100 PG carbon, it gives us this number, 33% top 3 meters. Then now, if you're familiar with all these retrogressive thaw slumps, with all these, you know, the mass movement that we have in stability issues that we have in permafrost regions, you can imagine that, you know, these carbons, they are really exposed to the atmosphere. So I'm not sure if you are scared enough, but we continue. Then this is the carbon map of Canada in terms of carbon. You see that, you know, these regions we consider as like permafrost on top of that. And you see that we have some regions which are really prone to carbon release. So another thing that I want to mention is this term, we call it positive carbon feedback. It means that carbon sink in permafrost becomes a kind of carbon source. Sink becomes source. And if we calculate, you know, a kind of top bottom, you know, permafrost thaw, we estimate that cumulative permafrost emissions could reach 150 billion tons of carbon by the year 2100, by the end of this century. And this amount is nearly half the world's remaining carbon budget. Half of, you know, half the world's remaining carbon budget if we want to keep warming under 2 degrees. see the importance of that. And I remember last year or 2 years ago, I saw it, a kind of greenhouse gas emissions. It was a chart from different industry, from different sectors, and also what scientists expect if we want to meet that, 2 degrees warming. And there was a kind of 10% difference between the predictions and the reality. And I remember in that article, I couldn't find it to present it to you today, but it was something we don't know from where that 10%, that 10% come from. And one of the assumptions was maybe it's due to permafrost carbon feedback. Then today it contributes to 7% of carbon release coming from oil and gas, industry. But I am sure that in the coming years, we will hear more and more about the impact of permafrost carbon feedback. Yeah. So again, the image you can see here shows soil organic carbon pools across, this northern circumpolar region. And the other thing I want to mention is that the complexity of the problem. We have temperature rise, climate change, but again, the ground surface temperature will not necessarily follow the same trend. Why? Because of soil type. Second, because of the presence of the snow cover. For example, if we have shrubs or another, for example, vegetation type, it can also impact, the ground, the warming, at the ground. And the bad news is that even today, we are not sure about that. There's no agreement regarding the impact of vegetation on permafrost. Does it, does it keep the ground like cool, or it will contribute to warming? You can find, both theories in the literature. There's no agreement between, these things. Should we plant trees up north in northern regions to stabilize permafrost and fix carbon? There are some people, researchers, scientists that said, no, don't do that, because that vegetation or afforestation will contribute to, the ground warming and carbon release. So today, I just want to tell you the complexity of this phenomenon. We have temperature rise, we have different patterns of moisture content, and the release of CO2 to the atmosphere. Greening of permafrost regions will increase soil, what we call it soil respiration, which is a key ecosystem process that releases carbon from the soil in the form of CO2 or sometimes methane. Then soil respiration refer to production of carbon dioxide when soil organisms, those tiny microbes, breathe. We divide it into 2 parts, autotrophic and heterotrophic respiration. Then autotrophic is that when oxygen is really available and the emission of CO2 from plant and roots respiration. The other term, heterotrophic, it's related to microorganisms breathing. And this is related to CO2. We also have methane emissions from permafrost, which is caused, by microorganisms. We call them methanogens. That those organisms produce methane as a metabolic byproduct in hypoxic conditions. Hypoxic, it means low oxygen, level. Sometimes we have methane, coming up from permafrost, and in the way oxygen is available, then methane becomes, in form of CO2. And the bad news about methane is that in terms of warming, climate warming, the impact is like much worse than, the CO2. And these plants and microorganisms, they are not like independent. They like they live in a kind of symbiosis. They are, there's lots of connection between them, dependencies between them, and they influence their activities. Then here you can see actually the really rough, not rough, it's detailed, but what I want to tell you is that interconnection between different phenomena and the impact of vegetation. Again, lots of uncertainties on that. Really, the contribute to increasing, microorganism activities, maybe because those roots, like they act like nutrients for microorganisms they approach, but at the same time for their own growth they need more oxygen, they need more like nutrients. Then it can actually reduce the activities of microorganisms. Then as you can see here, in green we show the increased activity, the blue line shows the decrease, and sometimes we have like contradictory, the processes and mechanisms. They are in competition. Which one will win? We don't necessarily know. But again, microbial activity, vegetation growth, and different types of microorganisms we have, or just present that autotrophic and heterotrophic, which are related to aerobic processes, and also we have methanogenesis and fermentation when the oxygen level is really low. And all of these mechanisms contribute to greenhouse gases emission. Here also you can see at a little bit at bigger scale than when we have the creation of thermokarst. And why I'm saying thermokarst, because hydrology, the water access is also another important factor. Why? Because it affects directly the level of oxygen in the ground. Then all of these mechanisms have strong impact on the activities of all these tiny microorganisms that contribute to permafrost carbon feedback. Then if I want to present the key processes driving permafrost carbon feedback, as I again told you, different actually the factors can have an impact on that. For example, we just talked about microbial decomposition, microbial activities. Something which is also very interesting, and unfortunately we cannot really find the data in the literature on that, even in the laboratory scale, is that the impact of freeze thaw and also wetting and drying on microbial activities. What we know is that Q10 is a parameter that we use to describe, the microbial activities. For example, we say when temperature increases by 10 degrees, what is the increase in activity of microbial, microorganisms. What we know is that if we go through like freeze-thaw cycles, that Q10 increase up to 20. Imagine from like -5, you want to go to +5. You can see that Q10 increases like in an exponential way. We do not have, such trend when temperature goes from 10 to 20. It's normally like 1.5 to, the factor of that. But from negative close to 0 degree to positive, you can see how rapidly, these microorganisms become active. The other thing is the impact of moisture. Then here we talked about the impact of temperature. Moisture also controls, as I told you, oxygen availability. Then it can affect, the production of CO2 versus methane. The other thing is plants microbe interactions. Here you can see in that region, which impact root respiration, and also the other phenomenon, we call it rhizosphere priming. And thermokarst formation exposes deep carbon-rich layers as well. Again, carbon becomes more available. We have water, so we have temperature, we have like warming also. Then everything is in favor of carbon feedback, carbon release, greenhouse gas emissions. The other factor I want to mention is that the spatial and temporal controls. Again, the bad news is that if we really want to study permafrost carbon feedback at regional scale, and again, even in a laboratory, time matters. We've started, monitoring different sites. Now you can find many references in the literature in recent years, 2024, 2025. But if we really want to have a good understanding of the impact of climate change, vegetation, landscape changes, thermokarst, everything, we need to have at least like 5-10 years of monitoring data. 5 years to me, again, it's not too much, but a few decades of monitoring data, which unfortunately is not really available. And if in some locations you can find, such information, you cannot really generalize it to other regions. Then you see the impact of time. The creation of thermokarst take time. Vegetation, landscape change takes time. Then you see time, and again, the impact of like spatial, controls on that. Site, from site to another site, it can also changes. So how we can model, such complex phenomena? There are 3 approaches that scientists and engineers have been using. One of them is empirical models, as it's evident by the title, is that we normally use statistical relationship and observational data. And the problem is that we cannot really generalize it to other sites. We also have physics-based models. We go through the conservation laws and all these, the processes controlled by the physics. One of the drawbacks of this technique, this approach, is that, what is going on at really poor scale? Sometimes we cannot really like model it through mathematical, the models and equations. Those microbiological mechanisms, biogeochemical mechanisms. So we have another approach, we call it process-based models, which is based on this, I don't want to say based on that, but mix, these physics-based models with like some empirical models that we can at least answer some questions. Here again, you can see the different process-based methods available in the literature. What that THBGC model, it's the model that we've developed in our lab, and I'm going to present it. We tried to actually answer some fundamental questions that other models, I don't want to say neglect, but because of the simplicity, sometimes we try to not consider, some factors in the model, but we tried to actually address first of all, a spatial resolution. It's a model that works at like centimeter level, even at pore scale level. We try to see what's going on in a pore, and then how we can actually generalize it to a site. For now, it is limited to one-dimensional analysis, that warming from the top. And we tried to consider the impact of freeze-thaw titles, the presence of different type of gases, including oxygen, CO₂, and methane, and different, the complex gas transport that we may have in reality. So we have 3 phases: air, liquid, solid. And we have, you can see different components. We have soil particles, as you can see. We can have water and ice, and also we have 3 gases: methane, carbon dioxide, and oxygen. And If I want to present now our model a little bit, I'm an engineer. No one is perfect. Sorry for that. I have to show you some equations and mathematical framework, but yeah, be patient, please. I try to skip it. Then we have thermohydraulic model. We have gas model in our model, and here you can see our assumptions. We don't study here permafrost stability from mechanical, viewpoint. Our assumption is that we have no mass loss, we have no retrogressive thaw slumps in the model. What we have is that soil is stable, permafrost is stable from mechanical viewpoint, but we want to study the impact of temperature and precipitation, water movement within the soil. And also for the gas model, within each soil layer, we assume that gases reach rapid equilibrium between the water field and airfield zones. Gas trapped within the ice we didn't consider in our model. And also the advection term for gas transport is explicitly accounted for methane, as it is the dominant gas undergoing evolution in water field pools. So the equations, then we have mass conservation. We considered phase change, as you can see. Theta here shows water content plus ice content. And QW is our flux that we modeled here. If you are in geotechnical engineering and you're working on saturated soil mechanics or frozen soil mechanics, you probably are familiar with some concepts. But these are the ways that we define, the water content. We used Van Genuchen model, which depends on the suction. It's the term that we defined here. And we consider two types of suction. One suction which governs, the presence of water and ice in the soil. And the second, suction is really related to liquid water. So through mathematics, we can obtain that pressures or suctions which are related to pore water pressure. We can relate those pressures and suctions to water content and ice content. Then we have also temperature freezing depression, as you can see. And we use this hydraulic conductivity model to obtain, our flux, water flux here. For energy conservation, we deal with everything related to temperature, energy level of the ground. Then CAP is apparent heat capacity of the soil. Then we have different phases, as I told you, solid skeleton, solid particles, water, air, and other things. Then that apparent heat capacity includes all of these, as you can see. S is for soil particles, A is for air or gas, I is for ice, and W is for water. And we also consider the impact of freeze thaw, phase change on that apparent heat capacity. And here you can again see that flux, energy flux, and our, conductivity coefficient. So based on that, we also considered conductive flux in the ground and also convective flux in the ground. We defined all of these, physics-based phenomenon. And for now, the mass conservation of gas in terms of gas concentration, we use this equation. In the parentheses, you can see that we defined different type of flux for gas. For example, the first one shows the flux of the gas due to diffusion in the air. The second one shows the flux caused by dispersion in the water. The third one shows the flux due to convection in the air, and etc. Then for each parameter, we also define, an equation to be able to relate the chemical concentration to flux through these equations. And if I again come back to our first equation, you see that we have another term which is S, and we call it kind of source and sink terms. Then carbon, methane, as I told you, permafrost, sink, permafrost, carbon, sink, carbon source. It's all related to these coefficients. For each gas, CO2, methane, and oxygen, we define it. We tried to consider, again, autotrophic and also methane, production, soil respiration, microorganism activities. So these are things that we cannot really, like mass conservation, the law of physics, go through that. We have to use some empirical relationship. We have to, have data in the literature. We observe and we see how we can, develop, an equation, a formula for such phenomenon. But just to tell you, in these equations, you can see methane production source. We can have methane consumption sink, methane transport. The same thing for carbon dioxide. Here you can see that we define all these, different terms. Methanotrophy is what I told you. We have at first like methane emission, but in the way it becomes in terms of carbon release due to some chemical reactions. Autotrophic respiration and microbial respiration, and the same thing for oxygen. Oxygen processes in the source terms that we define in our gas equations. So we considered all of these equations, governing equations, we implement in a finite element code. Thanks to my PhD student, she's a very brilliant lady. So we tried to implement in a finite element code that we developed in our lab, and it resolved the problem in a sequential way. Because the problem, as you can imagine, is highly nonlinear. It's highly nonlinear. We have lots of convergence issues. Then first of all, we go through heat and mass transfer. We make sure that it converges. So we continue. We have mass conservation for all those three gases I told you, methane, oxygen, and CO2, different phenomenon as I presented in those S terms. And then we solve it and we get number that shows greenhouse gas emission, the level of that. In the numerical model, we also need to have our boundary conditions at the surface. What's the level of warming? Should we keep like constant temperature? Or if we want to model until 2100, how we can consider that trend of climate warming at the surface? And also, what are the initial conditions of the model? So you can imagine how our model depends on a specific site. You use it, for example, somewhere in Nunavik, but when you want to change it to someone in Nunavut or in Alaska, you have to adapt. But the physics is there. Physics is there, it doesn't change. You only need to change boundary conditions, initial conditions of your ground, and also those source terms that I told you. Sometimes it's really site dependent. We need to have data to be able to calibrate them. We find, a site, as you can see here in Northeast Greenland. It's a study, I think 2018, as you can see here. We found this paper that we could find some information about this site. We did lots of search to have an idea about the site properties, the parameters, what is the density of solid grain, porosity, all of these parameters. Sometimes it was common sense. For example, you have this type of soil, let's consider that level of hydraulic conductivity. Then we try to build up our model. This is also, the boundary condition we considered, also the initial conditions that we assumed in our model. Some information was provided in the paper, we took it. Some other parameters, as I told you, we did a search in the literature and tried to find, parameters close to the site. And some, parameters, we had no choice, we just assumed. Then here you can see the differences between our model, which is shows in red, field data, the green, dots, and another process-based model that you can see here, ISBA methane model. Then you can see that how close our thermo-hydro-biogeochemical model is to the field data, at least for this specific site. Then we took our model and we applied to two different sites. One of them is in Nunavut. You can see here the site, and the other one in Yukon. I'm just going to show you some preliminary results related to Nunavut. And as a boundary condition, do you remember in my first slides, I show you in Nunavik, north of Quebec, ground surface temperature, different locations. We use our AI model, train it with available data to have an idea about the ground surface temperature in these specific sites from 2006 to 2100. We tried to run our model since 2006 to make sure that our model is less sensitive to initial conditions. Okay, then 2006 to 2100, we run the model, and here you can see the terms of CO2 emissions and methane emissions until 2100. There are some rough, the results that we got. Here you can see that during the early 21st century, the Nunavut site acts as a net carbon sink. Both CO2 and methane fluxes remaining negative due to low soil temperatures and maybe limited microbial activity. Here, the first part of the model. Under RCP 8.5 scenario, this sink behavior reverses around mid-century here. And in comparison, RCP 4.5 emissions remain near neutral or only slightly positive after 2060. I'm not really worried about RCP 4.5 because everyone, I don't know if it's good to say that, but we know that we should really, if we want to do climate change studies, it's better now to go with really RCP 8.5 scenario. For methane emissions, you can see that it remained negative until approximately 2060, and after which they increase rapidly. So these diverging trajectories show the strong temperature sensitivity of permafrost carbon release and also highlight the mitigation potential of stabilized climate pathways. Again, with all the uncertainties that I told you, earlier, vegetation type, snow cover, the uncertainties we have related to surface condition, vegetation, shrub, snow cover, how they impact actually the boundary conditions at the ground surface, the presence of thermokarst, for example. It gives us actually a very good foundation to find information, field data, and use our model, to study at a regional base. But at the same time, I have to bring to your attention the limitations that we have in our model, also in other models. First of all, here we assume, as I told you, gradual top-down thawing processes, which is not the reality in the field. The model is limited to simulating the active layer near surface permafrost. We do not consider that mass movement, retrogressive thaw slump. Then you can imagine top 3 meters, it's good to study, but if we really want to account, couple this carbon release with mass loss, it's something that we have to add to our model. Considerable uncertainty arises from limited knowledge of the spatial heterogeneity and vertical distribution. And also in our model, THBGC model, we only consider methane and CO2. Then nitrous oxide, it's something else that we should also add. And biological uncertainties, again, remain a significant frontier in our field of research. I have to acknowledge and thank my students, Nilufar, she's my PhD student, and Sophie, my postdoc, who contributed a lot to this work. Thank you very much.
Thank you, Pooneh. Thank you so much for sharing your knowledge and expertise with us.
My pleasure.
Yeah, permafrost carbon is really a significant topic that's been well recognized and studied. And this actually is our first permafrost carbon talk in our past 13 USP webinars. And we hope to have more talks on this important topic. Our audience, and thank you for attending. If you have any question, and feel free to type in under the Q&A button. And we have one question. Pooneh, could you read out and then try to see if we can answer that? Thank you.
Yeah, the Yukon site seems to have been plotted in Alberta. Maybe, thank you very much for your question, but I can assure you that it was in Yukon. And maybe that dot, the map, it shows like Alberta, but we studied in Yukon.
Pooneh, while others are trying to type their question, I have two questions to ask, please. First is the permafrost carbon pool you showed is based on the top 3 meters of the permafrost, right? And with the thawing of a permafrost and the warming and the thawing, the permafrost under 3 meters and below could also be exposed. Then will be more carbon could be exposed, right? So that really can the situation could be worse. Is that right?
Exactly.
Okay.
That was the whole message, that even with that top 3 meters, there are lots of uncertainties, and the numbers matter, especially when we talk to public and politicians, the importance of permafrost stabilization, etc. Those numbers, when we say half of the remaining carbon budget, top 1 meter, then it's the way that we communicate. We should really worry about that things, but the problem can be much bigger than what we expect, because as you said, we have thermocrust creation, we have like retrogressive thaw slumps. I mean, the carbon deeper, can also be exposed to release. And this is actually exactly, it shows the importance of the problem.
Thank you. We have another question from Thomas. Could you first read and yeah.
Yes, we did. Should I read the question? It's our permafrost.
Be good because I'm not sure if the recording would show the the
Yes.
question. Mm.
Yeah, sure. Our permafrost degradation models being truthed with information gathered from boreholes in undisturbed ground. Yes, we did lots of. I only showed you our verification with the field data. I mean, related to carbon. But yeah, we did lots of, the validation, verification scenarios for thermal, the part of the model, thermohydraulic part of the model. And yeah, we also validated our model, against boreholes data.
Thank you. Well, the permafrost carbon is also a very complex problem, and as you presented, and when you laid out the framework for the modeling of permafrost carbon feedback, and when you presented the equations, and well, no one left the webinar, so that's good to see.
Sorry
And
for that.
no, well, you mentioned there are physics-based and process-based modeling, and you also touched on the AI usage. But it seems like the AI application in the permafrost community is less compared with other field. So how do you see AI or machine learning can be used in this topic?
Yeah, it's a very good question, Professor Joe. Thank you very much. I don't want to be like, I don't know how to be politically correct, but what I want to say is that if we want to use meaningfully AI, we need to have data. And we need, at least if we want to use like physics informed stuff, we need to understand very well physics itself. In some fields, they have large data, they can use it. How many people enter, how many people leave, what is your blood sugar, these are just data. It's not physics behind that. So you can train your model, you can use the available data and get some, I don't know, conclusions from them. In our field, in the study I showed you, we used AI only for ground surface temperature. And we developed it by admitting that N factor is not enough. Energy balance is not enough. We understand the physics, but again, N factor is not physics-based. N factor is a way that we try to translate like air temperature to ground surface temperature. So we have lots of climate station. We have like, borehole data. We have enough to train an AI model. And the advantage is that if, for example, we keep using the same model in a specific site, we will have more and more data, so we can reduce the uncertainties on that. These are just related to climate data, air temperature, you have climate scenario, weather station, you can use it. But when it's related to modeling permafrost, I don't like it at all. I mean, we cannot use it. I mean, everyone can use everything, but what I want to say, I'm not sure that if we get like reliable, the data from the models.
Thank you. And also thanks to Jeff for reminding me that others cannot read each other's, I mean, our audience cannot read each other's question. I did not know that. And I need to change the setup so that we can read each other's question. But we have 3 questions.
Yes.
Pooneh, if you can read and then answer them if you have time.
What time step does your model run on? How does it represent vegetation? Time step can change from seconds to days to months. It's really up to us to define it. Then we only need to be compatible. I mean, if, for example, at the boundary condition, we have daily data, we should make sure that, through interpolation or other techniques, these time steps match. But our model is not really limited to specific, like, as I told you, it can go from seconds to days, months, yearly, the basis. It depends on the convergence. And also the accuracy of our model. In what I showed you, to be honest, I have to ask my PhD student, but I think from our discussion with her, I think, again, I repeat, I'm not sure. I think it was daily basis.
And we have, I'm mindful of everyone's time, and we have 2 questions. Pooneh, if you can read them and answer them briefly, I'd really appreciate it.
Yeah, how can the carbon quality from permafrost soils affect the emissions of the model results as the permafrost thaws? I think carbon quality, I think you mean CO2 or methane, I assume. Our model will not be affected by that. Our model is able to distinguish between carbon and methane. If field data are available for soil parameters, that would be really helpful. But again, I don't know if I answered correctly your question. Sorry for that. I didn't really understand your question. Will your method enable the amounts of both sea-bearing gases to be estimated in any permafrost zones? And have you done any work to determine how much area around single soil test? Yes, the advantage of the model is that it's not empirical, it's like physics-based. We have conservation laws, then you can adapt even on Mars. There's no big, but the big problem is that how from field data we can calibrate and get soil parameters from that. We studied in Nunavut and also in Yukon, and you can apply it to any other sites. And also for now, it's limited to 1D. The modeling from single soil column field test, but it can only for now calculate from the ground surface to bottom.
Great. Hey, thank you again, Professor Maghoul, and for sharing your time and expertise, and we thank you. So
Okay,
yeah, that concludes our webinar. Thank you all for attending.
thank you very much. Thank you.